Hi, today we'll learn how to count leaf nodes in a binary tree. Basically, a leaf node is a node that has no left child and no right child. Let's take this example. Say if we have 10, 5, 20, 15, and 30. Here, nodes with values 5, 15, and 30 don't have any left or right children. Therefore, 15, 5, and 30 are the leaf nodes of this tree. Now, coming back to the question of counting leaves in binary tree, we have two approaches. The first is the recursive approach, and the second is the iterative approach. So the recursive approach is also known as the depth first search approach, and the iterative approach is also known as the breadth first search approach. So let's first understand the depth first search or the recursive approach. In the recursive approach, we need to break the problem into smaller subtrees. Each node returns how many leaf nodes exist below it. So there are three cases in this. The first case is the no node case. Like if node is equals to none, then we simply return 0. The second case is if node E is a leaf, if it's a leaf, then we simply return 1. And the third case will be we simply add the left and right subtree counts. Okay, so these are the counts of the leaves. Okay, now let us look into the recursive breakdown. So basically the root asks its left and right child how many leaf nodes do you have. Okay, so let's say we have count of 10, we have count of 5, and then count of 20. Okay, if left equals to null and right equals to null, it means it's a leaf node, so we simply return 1. Let's resolve the left subtree here. So we have node 5, but it does not have any children, so it directly returns 1. Now let's resolve the right subtree. We have count of 20, that is count of 15 and count of 30. Since this is a leaf, we return 1, and since this is a leaf, we return 1. Node 20 basically is not a leaf, so it asks both its children, both 15 and 30. It asks whether they are leaf nodes or not, or if they have any other children. Since their answer would be no, I am a leaf node and I don't have any children, they simply return 1 1. Now let's combine the results. Finally, everything bubbles up. Basically, the count of 10 becomes 1 from the left subtree and 1 plus 1 from the right subtree. That is 3. Okay. So total leaf nodes will be 3. Recursive depth first search works bottom up and it is very intuitive. So just remember this. DFS is bottom up counting. Okay. Now let's look at the coding part. All right, let's code up the DFS approach quickly. So we have defined a function count leaves that takes the root of the binary tree. And the first base case would be if the current node is null, there are no leaf nodes. So if root is none, then we return 0 because there are no leaf nodes. Now the second base case would be if both left and right children are null, this node itself is a leaf. So if root dot left is none and root dot right is none, we return 1. Why are we returning 1? Because that is a leaf and we got to return one leaf node. That's why. And otherwise, we recursively count leaf nodes in the left and right subtrees and return the sum. So the final one would be return count leaves of root dot left. This is for the left subtree, and count leaves root dot right. This is for the right subtree. Now let's go ahead and run the code. As you can see, for the first test case, we have 3 leaf nodes. And for the second test case, we have 4 leaf nodes. And for the third test case, we have 2 leaf nodes. Now let's look into the iterative approach or breadth first search approach. Now let's look into the iterative approach using a queue and a level order traversal. Let's suppose we have the tree as like in the previous example, 10, 5, 20, 15, and 30. And we have an empty queue here, and at the start we initially don't know how many leaf nodes do we have, so let's initialize leaf count to 0. We start putting the root into the queue. So basically in the queue we have the root node, and while processing a node in a queue we pop it and then check it. Now check 10. So 10 is not a leaf node. So what we do is we enqueue with children. So what are the what is the children? What are the children of 10? So the children of 10 will be 5 and 20. So basically the enqueue becomes 5 and 20. Okay. Now next we gotta process the node 5. So pop it. Since 5 is a leaf node, we increment the count to 1. And since we are left with 20 in the queue, we simply write the queue as 20 and the leaf count becomes 1. Now let's process 20. Let's check if 20 is a leaf node or not. No, it is not a leaf node because we have its children as 15 and 30. So basically we are popping it. We are checking if it is a leaf node or not. If it is a leaf node, we increment the leaf count. If it is not, we simply enqueue its children 50 and 13. Okay. Now let's process 15. Pop 15. And we got to check if it is a leaf node or not. Since it is a leaf node, we increment the leaf count by 2. Similarly, we are left with 30 in the queue and pop 30. So check if 30 is a leaf node or not. Since 30 is a leaf node, we increment the leaf count by 3. Our traversal basically ends when our queue becomes empty. So after popping out 30 and processing it, our queue basically becomes empty. So we stop our traversal here. So the final leaf count will be 3. That will be the answer. So in summary, we have a recursive approach and we have an iterative approach. So recursive approach follows depth first search approach and iterative approach follows breadth first search. Both the approaches are correct and efficient. We got to choose depth first search for simplicity if at all we need it, or we can choose breadth first search when you think the recursion depth is way too risky to approach. So let's get into the coding part for the iterative approach now. Now let's implement the iterative approach. Let's first import DQ to perform efficient queue operations. So from collections, we import DQ. Okay. So now we have defined a function count leaves here with which takes in root as the input. And the first base case would be if the tree is empty, there are no leaf nodes, right? So if root is none, we return 0. Now that case is over. Now we got to initialize the queue and push the root node to it. So basically queue is defined as dq of root. So the root is pushed into the queue. And we also need to initialize a counter to keep track of the number of leaf nodes. So let's say we have leaf count initialized to 0. So this particular variable will store the total number of leaf nodes. Now we run the loop until the queue becomes empty. So that is our condition. So while queue, we remove the front node from the queue, that is current is queue dot pop left. Okay. So if the current node has no left and right child, it is a leaf node. The condition for that will be if current dot left is the current dot left is none and current dot right is none, we increment the leaf count. So leaf count plus equals to 1. And if the left child exists, we add it to the queue. If current dot left, we simply add it to the queue. Queue dot append current dot left. Okay. And the other case will be if current dot right, we add queue append of current dot right. Okay. So basically left child is pushed into the queue, and then if right child exists, even that is pushed into the queue. Okay. And after the traversal is complete, we kind of return the final leaf node. So we simply return leaf count. Okay. Now let's go ahead and run the code. As you can see, for these test cases, we are getting the right output. Like for the first test case, we are having 3 leaf nodes. For the second test case, we have 4. And for the third test case, we have 2 leaf nodes. Thanks for watching.